I wanted to show you a little bit more about electric charges and the forces that are associated with them. We've already talked about Coulomb's law, which is, I'll rewrite it here. Oh, I should say Fe. Stay consistent. And this gives us the size of the force associated with two charges, whether they're positive or negative charges. And the question is whether they're attractive charges or repulsive charges. So I'll say Q2 in this case is positive, and I'll say Q1 is a negative charge. So if this were the case, I could, and knowing the distance between them, I could figure out what the size of the force is. Now, whether the force is to the right or to the left depends upon whether the charges are attractive or repulsive, and in this case, they'd be attractive. So both charges would experience the same size force, but directed towards each other, like this. So I'm going to erase this one over here. That would only be true if they were repelling each other in this case. So both charges would be attractive, and we could figure out the size of that force, which we often denote the size of the force by the length of that arrow. So however long that arrow is, and these arrows should be the same length because they denote how strong the force is. And the direction of the arrow, of course, is associated with the direction of the force that the charge experiences. So this one would be to the left, right here, and this one would be to the right. And I mentioned in class, perhaps, I think I did, that when a force is directed to the left, we're saying that would be we denote the direction by negative I hat, and to the right by I hat. So let me give you an example of this, and we'll then take this a step further and go with the vertical direction also. But let's just say that Q1 is equal to, let's see, 1 microcoulomb negative, and Q2 we'll say is equal to, I'll go with plus 2 microcoulombs. I can find the size of the electric force. That would be Fe. It's equal to 9 times 10 to the 9th, which is K, times absolute value of negative 1, which is 1 microcoulomb, or 1 times 10 to the minus 6 coulombs. And Q2 is 2 times 10 to the minus 6 coulombs. And let's just say the spacing between the two charges, I'll say R equals 30 centimeters. And so I take 0.3 meters, because I have to convert 30 centimeters to meters, and I'm going to square it. Okay, so then I do the work of doing this. On top I have 9 times 2 times, just reordering what is being multiplied by what. And on the bottom I have 0.3 squared. So next step. Got 18 times, on top 10 to the 9th times 10 to the minus 6 is 10 to the 3rd, times 10 to the minus 6 is 10 to the minus 3rd, divided by 0.09, which is 0.3 squared. I'll rewrite what the bottom is. It's 9 times 10 to the minus 2, because that makes it easy to see. 18 divided by 9 is 2. 10 to the minus 3rd divided by 10 to the minus 2nd is 10 to the minus 1st. So that gives me 0.2 newtons. And this looks familiar, perhaps, because you might have seen an example like this. All right, so that's the size of the force that both charges experience. Even though one charge is bigger than the other, both charges experience the same size force. Now the question is, what's the direction? How do I write it? I could certainly say, okay, this one on the left, let's say Q1, experiences the force to the right, and I could write 0.2 newtons. And the other one, Q2, experiences a force of 0.2 newtons to the left. So I certainly could write that, but I don't necessarily want to have to draw a picture each time I want to express the size of a force. So what I could do is I could write it using the I hat and j hat. I could say Fe1, which is the force that charge Q1 experiences, is equal to 0.2 I hat, because it's in the plus x direction. And Fe2 equals 0.2 times minus I hat, because it's pointed to the left. But it makes so much more sense to put the minus sign here. So I should write it like this. Should always have the minus sign right out in front and open so you can see it. It's easy to miss it in there. And just have the I hat at the end. Let me erase that parenthesis, I don't need it. And what's interesting here, this is the positive charge, notice, Q2 is positive, but it experiences a force, in this case, that's to the left, so it's going to have a negative sign in front of it there, even though it's a positive charge. This sign has nothing to do, whether this sign in front of the force is positive or negative, has nothing to do with whether the charge itself is positive or negative. It only has to do with the direction of the force that charge is going to experience. So in this case, notice the negative charge happens to experience a force that's plus I hat, or plus 0.2 I hat, and then positive charge happens to experience a force that is negative 0.2 I hat. Keep that in mind, so don't let the sign of the charge dictate the direction of the force directly. You have to look at what direction the charge would be pulled or pushed by the other charge. Okay, that's enough for this video and this example.